So I guess for the exam, here's the main points I want to hit. So I want to see that you can do a thermochemistry, you know, which is the delta H of formation, delta G of formation, and these standard enthalpies of formation, and S entropy. Those values that you can find in the thermodynamics tables to then calculate the delta H of reaction, right? Products minus reactants, etc. Okay, so that's pretty straightforward. And then this also leads to the vocabulary surrounding that, like exothermic, endothermic, exergonic, endergonic, and whether entropy is increasing or decreasing. We don't really have entropy doesn't really flow out or in. It's just the products have more entropy or less than the other. So we wouldn't really say exentropic or endotropic. That would be a way to make up that word, but I don't think it makes sense because we don't have entropy flowing anywhere. Heat flows, or energy flows, but entropy doesn't really flow. It's just a final state versus initial state. But you could say that the entropy increased or decreased by looking at whether the entropy was greater than. If it increased, it would be positive, a positive change. If it decreased, it'd be a negative change in entropy. And you need to be able to analyze why you think that's the case. So, let me just make sure that's in all. Let's, which, which has more entropy, just in general? Ice, water, or steam? Which has more entropy, ice, water, or steam? Okay, good. Yeah. And you can also think that entropy increases with temperature. So the hotter the object, the more entropy it has. Okay. Now, in general, all gases have more entropy than all solids and all liquids. Okay. So that's your background knowledge or baseline knowledge for entropy. Okay, so then we have the heat capacities, and we'll use the equipartition, right? Okay, so that big word, that was the limit when we were doing the initial ones. We did the partition function, we calculated it explicitly, but when we had high temperature assumptions and so on, then we moved into what we called the equipartition, meaning there really wasn't any statistical difference between any of the energy levels. And so the limits of those were 3/2 R for translation, 3/2 R for rotation if it's a nonlinear, and then 1 R for every vibration. But we realized that at room temperature, we don't really have any vibrations that are active except in larger molecules. So that's that 3/2 for trans plus 2/2 if it's linear, 3/2 if it's nonlinear. CV. Okay, and then plus R equals CP. And so then we need to calculate gamma. So you need to know these things pretty quick because, anytime you're doing calculations, you can't waste a lot of time. Once you get gamma, instead of making you do the full Carnot cycle or any other kind of cycle, I'm going to ask you to use the adiabatic relationships. So don't just focus on the temperature volume one. Be able to do volume pressure or temperature pressure or volume temperature. There's, those pairings. We have P, V, and T. So there's 3 variables. And so if I change temperature, how does the volume change? That's the TV, variable. But if I change the temperature, how does the pressure change? And so on. So you need to be able to use gamma. I have all of those in the notes, so put those all three in on your note card. There's really, you could say that there's really six of them, but if you know three of them, then you can just invert it. Like that one we had, I can't remember, but you had like T A over T B. I don't know, to the gamma. Don't quote me on this because I have to go V. Let's see, TB. Yeah, VA over VB, and then to move it around, you'd have VA to the gamma to 1 over gamma, right? VB equals TA over TB. What I'm trying to show is if you move gamma to the other side, it's 1 over gamma. You invert it. Say again? Here, yeah, but is it gamma minus 1 up here too? It might be. Is it gamma minus 1 like this? Because if we volume temperature, yeah, so I don't have the pressure one on here, but I'm saying like you only have to probably write down one of these is what I'm trying to say because you can get the other. That's my point. Yeah.
Yeah, pressure in so pressure.
Yeah, so you're talking about VP relationship, volume pressure relationship? Okay. Yeah. But is this one correct? Okay. Yeah. So, and make sure the A's and B's are correct. The A's on top and B's on bottom, or I mean, it doesn't matter if A or B is on top, but make sure that if A is on top here and TA, like make sure this one matches this one, because that can be a mistake if they're inverted. And so these might be actually inverted. So they are. So this should be B on top probably and A on bottom. Yeah. That's why I allow a note card, because I don't even have them memorized either. I've become, well, I mean, I guess my whole career I've decided not to depend upon my memory very much because, I mean, for vocabulary, of course, but like for equations, I always look them up. Even if I'm 90% sure I remember. Now, of course, the PV equals nRT, that doesn't count. But for something like this, where you got a bunch of little options, gamma minus 1, 1 over gamma minus 1, and all of that, I always go and check those out. So make sure you have an accurate note card and you know how to use it. Okay, so that's adiabatic relationships. Some conceptual things. Okay, 5. I would say recognize the differences between an isotherm and an adiabat. The main one being that if you've got a PV plot and it's not a Carnot cycle, so you're like, oh heck, now what, right? Because you've got the Carnot cycle memorized, but then I give you something different. This is what threw them last year. I gave them a cycle that looked like, I think it looked like this. It was half of a Carnot cycle. Just 3 legs, and they had no idea what to do with it. Okay. So here, this is straight across on the p-axis. What is this one called? This straight line? Isobar, yeah, isobaric. So this is an isobar. And then I've got 2 curved lines. One of those is going to be an adiabat, one is going to be an isotherm. And so you've got to figure out which one is which. Like this is your background knowledge. The steeper one is the adiabat. Exactly. So that means this is the steeper one right here. Okay, so this one is steep, so it's the adiabatic curve. And so that means that this one is the isotherm. And now you can look at your note card and see what kind of equations you need to do to calculate the heat, the work, and the state variables and all of that stuff. Okay. Um, Also, if we're looking at this, this may be the volume, or I think this was the volume that they needed to calculate, or the temperature that they needed to calculate. Like maybe they could read the volume off the chart. Like you've got your three volumes here. Um, the isotherm, this volume and this volume have the same temperature, and so you could calculate the pressure using the isotherm. But what about this one? What is the temperature at this point right there? That's the hot temperature. And you have to use the adiabatic relationship to get that temperature. So that's where this would come into play. So I was sad because I gave them a simpler problem, only 3 legs instead of 4, things to go faster and so on. But they were just looking at it like, I don't know what to do with this. Yeah. And so that's the skill. I mean, I really want y'all to exercise your figure it out skills. Okay. So that's something that I think is really important for chemistry students. When you get out, I mean, you're in a degree plan that when you get a job, you're going to be hired to think, right? There's jobs out there that you might imagine the boss coming in and saying, "I'm not paying you to think, I'm paying you just to do," right? Um, Unlock the door at 8, ring up the customers, and so maybe there's still some thinking done in retail. But my point is, fill these trays and move them on to the next thing. I mean, that's, you're not paid to think. But chemists, they're paid to think. In fact, HP came to Oregon State when I was a TA and was interviewing our students. And they said, "We really probably don't want any of your students, but we're going to give them a try." And I was like, "Why?" And he said, "Because chemistry students are scientists, and we don't want scientists." As, yeah, they had a printer factory in Corvallis, Oregon, and they didn't want to hire chemists because chemists were scientists. They wanted to hire engineers. And but they weren't designing anything. They said what happens is the chemists are working on the conveyor belt or whatever the assembly line is, and they're always thinking, how could I do this better? And they're like, we do not want that. We've made it as good as we can get it, and we want you to follow the instructions. So even if you're doing something that could be done better, more efficiently, don't change anything because you're ruining the quality of our product by changing things. And so yeah, now with more lean manufacturing, I'm sure that they have suggestion boxes, but still, you can make your suggestion in the box. Don't change anything on the assembly line, So that was an awakening to me as a grad student. I was like, you don't want people to think? And he was like, no, we want them to come in and follow the procedure and do it the same every time so that our product is the same every time. Yeah. So anyway, working on your figure out skills. So I'll have something like this kind of problem where there'll be a piece of missing information and you've got to figure out what you got to do to find that piece of information. So it's not too intimidating. It's not, my goal is to not let you run out of time, but still to get an idea of if you know your material or not, and if you can figure some things out. So that's 5 is recognize the differences between isotherm and adiabat. And then 6 would be calculate the missing information. As far as the content, I mean, use the homeworks as a guide. So I've got in this little thing all of the different homeworks. If there's any questions you have about any of them, got some of these worked out. It's a cute little cat. I remember drawing that. This is from last year. I just didn't delete all the work. Yes. Hmm.
And then some tribute link ties with
Yeah, that'll be the missing information. It won't be the whole thing, but like it might be the state variables table and you've got a missing number and you've got to decide, do I need to use an isotherm to calculate that number or can I use an adiabat? You know, which one of those do you need to use? Hmm. Yeah, I'm thinking the Excel, actually, I'm kind of questioning the 15. I think it should be more because that's recognizing, huh? You totally agree. Okay, yeah. You know, because I mean, I want that to be serious. I want you to work hard on it, and I want you to like really understand how the system works. And I don't want you again also to run out of time on the exam because I hate that because I don't feel like I got to know what you know, right? And so, um, I don't know. You know, I might do 20. It's pretty reasonable. Yeah. Now you got to really be I mean, you got to be honest about it. I don't want somebody working with anybody else and not learning the material. That's the only risk that I feel on my end. It's like I don't want you just looking over someone's shoulder and not really learning how this stuff works. Okay, so you know if you have a question, you're like, how did you do this or whatever? That's okay, but do your own work, learn your own material. You're cheating yourself, is what you're doing. It's not about the grade. I know grades are important, but yeah, don't hurt yourself. So yeah,
could be
yeah. There's some like error connect traps, I would say, if you're programming and you have a system and you put in the wrong number and you get NA and everything breaks, you need to put a trap in there for the errors. And so that section you really don't have to have the error trap section because I use that to make up exam questions and examples for class. And so I wanted to make sure that I don't use a temperature that's too high. And so I want the spreadsheet to holler at me, you know, and give me ridiculous results. Now you can kind of see ridiculous results in the two efficiency equations. No matter what temperature you put in, you could calculate the efficiency with the temperature. But if you put too high of temperature in to the state variables table and calculate the energy in and outs, the efficiency looks ridiculous, like it breaks. So there is a error trap at the end, but I kind of wanted an error trap earlier so I could see that I'm trying to calculate a state variables table that doesn't make any sense. Yeah.
so we gotta do that.
No, you don't. Yeah. Play around with your spreadsheet once you get it built and see where, like when it breaks, like if you're typing in the numbers and it starts to give totally crazy results, it's because your variables, your temperatures or your volumes or something don't make sense. So yeah. And it has to do with that adiabatic relationship because that's we're calculating like in our example, the volumes using gamma and heat capacities. So we're not explaining. Yeah, it's creating unrealistic. Like if you look at the diagram, you tried to plot it, it would break the plot essentially. So um, I don't know how to explain it. Maybe you'll see when you play around with it. I could pull up the spreadsheet and I could take away my error traps and see. So let's do that just for grins. It does need a plot. I wanted y'all to go ahead and figure that. I mean, it's in the video about how to make it. So let's pull this one up. There it is. Okay. It's where are you? There it is. All right. So this is on the video now. So let me go up here and I'll type in some bogus temperature. Okay, so max temperature says is 2649, so I'll go 2650. We'll just barely go. Well, let's do 2649 actually. Let's do that. Nope, it broke. Look at my plot. It went away. You see the plot over there on the right? 2640. Let's not do so bad. Let's go 1000. Okay, it's back. 1500. See, look at that 80 bat. These two 80 bats are dominating. They're getting closer and closer together. Then we've broken the group cycle. 1500, 1600. Let me just make that chart smaller so that we can. Yeah, so here we go. So as we make the temperature higher and higher, the adiabats have to be longer because the max and min temperatures are connected by the adiabatic curves. And so if they get longer for this to continue to be a cycle, the isotherms have to get shorter. And so if we go too high in temperature, let's go to 1800, 2000. See, look how short the isotherms are. So if we go too high, then the adiabats essentially become the same. 2200, 2300. Yeah. So as we get close to 2400, so you can see a point where the Carnot cycle ceases to make sense. And that maximum I calculated is 2649. That's the maximum temperature, where basically you have two adiabats. You're using adiabatic expansion, adiabatic compression. You're going down in temperature, up in temperature. Yeah, and so what does it do to the efficiency? Let's try to see those numbers. We're at 77% efficient. Let's go to 2500. Still at 77.26. Look how close the little red dots are. Our isotherms are really short. See that? And then when we go to 2650, so we're 78% efficient. 2650 NA. Yeah, so I've trapped that error and said you've got a problem with your state variables. So control. Yes. Yeah, so I've got this text here. If A18 is greater than A17. But let's look at how I calculated that A17. So 16 maximum temperature. Yeah. So it's essentially taking the gamma minus 1, and I'm looking at A4. That's gamma. No, A4 is. Oh, the compression ratio. Yeah. So notice that's what's going on. So notice that this volume that's calculated, let me change the temperature back to like 1800. Okay. This volume right here, where my arrow's pointed, can you see the arrow? Okay. That is calculated using the gamma and adiabatic relationship. Okay. If I keep going up in temperature, it gets smaller than volume A. And that's the thing that breaks it, right? A has got to be the smallest volume. That's tied to the displacement and the compression ratio. And so for me to go higher in temperature, I would have to change the compression ratio. And so it's when that volume B goes below volume A, because it's moving to the left as I go up in temperature. When it moves below volume A, then it breaks the cycle, and that's why the lines disappear. Yeah. So that's what I'm using to determine, when volume B equals volume A, that's the max you can go. Yeah. Okay.
Very like what will be in?
No, I really don't. You can do Kelvin. People talk in Fahrenheit a lot. And your gauges are in Fahrenheit. And so I went ahead and put it in Fahrenheit. But yeah, you can do Kelvin. I would like this business here, the atomic and linear and nonlinear. Let's do 0% atomic and 50% linear and nonlinear. Okay. Oh, okay. So I have these using this percentage cell value. This is a little thing here. So the other ones I'd have to put in 0.5. Yeah. But if all of these are between 0 and 1, you can come up and hit the percent sign, and it'll set the format of that cell as percent. So it will multiply it by 100 and put the percent sign on there. Yeah. So looks like I'm above the max. If I had nonlinear molecule or linear molecules, so I'm thinking like CO2 and water. So I've got 50-50 CO2 and water in there after combustion. I don't know if it'd be 50-50, but that's what we've got here. Then I would have a different max temperature and different efficiency. That's interesting. And so then you can use this to kind of look at the science. So when we had monatomic gases, I could go up to get almost about 78% efficient before the volumes created problems. But with linear and nonlinear molecules, those adiabats are not as steep. Yeah, and so I can only go to 1,000 F instead of 2,600 F. Yeah. And I could only get 54% efficient. So that's what we were saying, that those monatomic, if you have a monatomic gas, that's the most efficient Carnot cycle you can get. We don't really do that to produce work. We use monatomic gases for refrigeration. And so refrigeration is just running a Carnot cycle or a cycle similar to it in reverse. So we put work in and we pump heat. So in the combustion engine, we produce heat and extract work. In a refrigerator, we put in work and move heat. We pump heat. So we're pumping heat from the warm reservoir, from the cold reservoir to the warm reservoir, because we're running it backwards. And then down here, you've got your state variables table. Again, this is the volumes and temperatures. Let's see, I think looks like I used the temperature volume. Here's the adiabatic relationship. So let me click on the equation. Yeah, so we've got the volume at C times the temperature at C divided by the temperature at B raised to the D12. So we scoot up here. D12 is 1 over gamma minus 1. I went ahead and calculated a cell for that since we're going to use it. Yeah. And so that's the adiabatic relationship for calculating VC. Yeah. And then we had to do the same thing down here for volume D. For some reason, I didn't use the the gamma minus 1 cell, I still have 1 over gamma minus 1, but okay. But still, it uses the temperature and volume at A, because A and D are connected with an adiabatic relationship. Yeah.
The like state variables table, like the headers of the tables.
Yeah.
they can take out
Okay, that's a
all
good
those,
question. Yeah, so right here, this is a merge button. So up here it says merge and center. So if I unclick it, then it's over here on the left, right? So
Yeah.
the state variables table. And so I typed what I want in here, and then I select this whole group and I hit the merge button, and it merges those cells. And that's nice to do. This little marks looks like they've got some little error messages here. So what does that have to tell me? Can you see? Okay, inconsistent for me. And that just does that because there's it's not in a column where it has the same formulas all the way down. So it's just warning me. Yeah, I know. It kind of helps, I guess. Like if you were down here, and you saw it on one of those, you're like, okay, there's something funky about that. You know. Okay, so now these guys. So here's the adiabats, and here's the isotherms. Oh no, adiabat there too. So look at how I calculate these. This is a little strange. Okay, so this is how I did it. I have to relearn every time. So I've got an index, which is the number of data points here. Okay, and it goes from the maximum to the minimum on each of these lines. And so I think I divided it into 300. It looks like 300 increments. So my plot has 300 increments for every one of those lines. Okay. Now this is the maximum value, and this is the minimum value up here. And so what I've done is I've said, okay, for this adiabat, I've taken this minimum value, B24, which is the volume at point A, and then A49. Then I have the index, A49 times this, where's the A3, anchored, A3. That minimum volume, okay, divided by A349. Yeah, the maximum. Yeah. So what I'm doing is I'm saying, okay, what increment towards the maximum volume am I? Okay. And at the very first point, I'm 0 the way to the maximum volume. 50% down, I'm whatever the halfway point is, 150 times that distance to the maximum volume. So that's one way to do it. For the other adiabat, let's see. This one I'm using the adiabatic equation. Okay. Using the points below and above. Oh, I see what it is. Yeah, so this should just be volume. I've got it labeled adiabat, but this is the just the volumes. I'm just going to call that volume range. And now I can use the adiabatic relationship with that volume range to calculate all of the adiabatic volumes and pressures, and then all the isothermal pressures. Yeah. So you can look at this video and see how I've done the equations. I'm sort of cycling through all of them. And so what we're calculating is the pressure for the BC leg, the pressure for the AB leg, the pressure for the DA leg, the pressure for the CD leg. And then these are the maximums and minimums. So for AB and BC, I've got the minimum of those two, And for the compression, I've got the maximum of the CD and DA lines. And then these are the two that are plotted in that plot. So if I click on the plot, you can see, well, thought you could. Have to click on it. Yeah, you can see these are plotted versus the volume over here. All right. So that's the spreadsheet tool. I think you'll learn a lot, or at least last year they did. They said they learned more doing that than just studying for the test and doing a homework set. So, yeah. Yes. Oh, that's a good point. That needs to just be liters. Yeah. Since we're calculating the moles, a lot of these are written in, oh no, yeah, that's right. So it should be volume/liters. Okay. That's the way it should be written. Good question. PV equals nRT. Once you get you have the temperatures set from the gold cells. So you set your temperatures. And you've got the volume A and volume C from the compression and delta V displacement. And then we have the max pressure up here that you enter in. And once you get that, then that's going to be the pressure at point A, 136. Let's see. Yeah, it's A5 divided by 14.7. Yeah, so it's just at max pressure converted from PSI over to atmospheres. And so now you have three variables out of four. So you solve for moles. Okay. And then once you solve for moles using the ideal gas law, we'll use this number of moles through the whole table. So that's straight down, not a problem. Yeah. And then you really only have to use the adiabatic relationships twice. And I use it for VB and VD using the temperatures because we've got the two temperatures. So I go to calculate those two volumes. And then you just use the ideal gas law for all the pressures. So you just go straight down. You've got number of moles now. It's like Sudoku. You're filling out the table. The only tricky spot in this whole table is the adiabatic relationships. And that's right. That's because it depends on the type of gas you're dealing with. And so you got to figure that out. So whenever I'm making a problem, I don't want to give you guys a Carnot cycle that looks like this because it's hard to tell. You can't even really see. Let me move these guys out of the way. Maybe can I bring this to the front? Okay. I don't want to give y'all a Carnot cycle that looks like this because the isotherms are almost invisible. So I would come over here and I would reduce the temperature, And that's a more reasonable Carnot cycle. It's still not like too big, like they're not too far away. Maybe I might make it 600. Okay. The only downside is that this adiabat and this isotherm down here look really, really like they have the same slope. Okay. But this isotherm is going to come up and it's going to be less of a slope than the adiabat. So this blue curve on the bottom would come out here like that and it would go that direction. And it turns to an adiabat, so it's steeper and goes up to a VA. We've got about 5 more minutes. What about any questions on the homework or anything like that? That you guys?
Elementary is going to be on the exam, but
It's really y'all are still in the middle of that lab, and so no, not really. I mean, there were some questions in the homework just to kind of prep you for the lab. Yeah, to make sure that you have a good experience in the lab. Let's see. Let me change this back to PowerPoint section. There we go. There we go. All right, so see if there's anything in here I want to emphasize. We talked a lot about this. Okay, let's say if we have one of those isobars, the isobar, this is the work equation, minus px delta v, and you're going to get your work in liter atmospheres. So remember how you get out of liter atmospheres to joules? Yeah, you take the ratio of the two ideal gas constants if you want, or you have on your note card 101.325 joules per liter atmosphere, and then you get to joules. Okay. Did y'all get caught by the trick question here? Which one was it? Oh, was it? Yeah, where it was the lid was fixed and there was no work because there was no change in volume. Yeah. Yeah, so the calorimetry is mainly for the lab. Yeah, so the specific heat for the stainless steel, again, 460 joules per kilogram per degree C. Per kilogram, so water would be 4,000 almost. I think, let's see, calorie would be 1 cal, then 4. Yeah, it's anywhere from 7 to 10 times more heat you can put into water before you raise the water a degree as opposed to metal. So water is a way better heat transfer medium. And so instead of letting the heat in the engine work its way out and having an air cooled engine, we use water. We run it through that engine and it carries the heat away way more efficiently, 7 to 10 times more efficiently. So that's why we do water cooling. And that's why some high performance computers, desktops have water cooling. I was always worried about that. I didn't want water inside my computer. And then here's the thermochemistry stuff. Just doing again products minus reactants. Now this one is really tedious because it's homework and homework's supposed to be tedious. But you got all these components. I'm not going to do this to you on the exam. It's a super simple one, but still you got to know how to calculate it. Right? But yeah, all these reactants and stuff. So again, just working with this isothermal expansion versus adiabatic expansion. Isothermal you could treat as a gamma equal to 1. So yeah, I can just show that to you. So uh, if we've got PV equals nRT and we do ones and twos, P2 V2 equals N2 RT2 divided by P1 V1 N1 RT1. Anything that doesn't change is canceled. And so if we wanted the VT relationship, then it's V2 over V1 equals T2 over T1. Okay. Or let's say it's an isotherm and we want to know the pressure volume relationships, then it would be P2 over P1. The N's are the same, the T's are the same, it's an isotherm. And so we bring the V1 over to the other side and V2. So you see it has an exponent of 1. So that's the isotherm, is the pressure volume relationship is like this, and it doesn't have a gamma up there, or you could say the gamma is equal to 1. If it's an adiabatic relationship, the gamma might be 1.3 or 1.4 or 1.5, whatever we calculated for the atomic, linear, or nonlinear gases. I think we're ready. Make me proud.